if you take a length of wire and you wrap it around into a coil, like wrap it really tightly to make sort of this loop coil, then you have formed a circuit element which is called an inductor. And an inductor is a device which stores energy in a magnetic field. So if you have a current that flows through this coil of wire, then there will be a magnetic field which is formed kind of inside of this coil. So you get a magnetic field which is formed here. And then you get some fairly interesting properties that arise because this magnetic field can in turn induce a voltage. And so this effect is called inductance, and we're going to study how this works. So the picture that you see on the left-hand side is a photograph of a real inductor, and you can see it's a coil of wire, and it will be wrapped around an iron core, and so the iron core kind of concentrates the magnetic field there, and so that's kind of the sort of optimal way of actually building inductors. Now the key properties of inductors, let's have a look at those. So first of all, they are described by an equation which looks like this. So we have a voltage on the inductor which is equal to a parameter L, which is called the inductance, multiplied by di dt, the rate of change of current. So let's define the terms in this equation where VL is the voltage on the inductor, I is the current flowing through the inductor, and L is the inductance. L is the inductance. So inductance is kind of how much of an inductor is this. So when we talked about resistors, we measured them in ohms with resistance. When we talk about inductors, we measure their inductance with a unit which is called a Henry. So L is measured in Henrys with the letter H. So you might have, for instance, a 100 millihenry inductor, for example. So L is measured in Henrys. The circuit symbol is a little bit like a coil. So we draw kind of like a little spiral, and that is our circuit symbol. You'll also sometimes see it drawn with kind of like little loops like that. So those are the circuit symbols that you will see for an inductor. And to label it on here, we have a voltage. So VL would be the voltage across this inductor, and then the current, IL, or just I in my previous equation, is the current that flows through that inductor. So let's actually study this equation and think about the implications for a moment. So one thing that we can recognize from this equation is there will only be a voltage if the current is changing. So there is only a voltage on an inductor when the current is changing. Right? The voltage is proportional to the rate of change of current. Constant current constant current equals no voltage. This is very different behavior to resistors. So for a perfect ideal inductor, if the current was constant, there would be absolutely 0 volts across that inductor. Another property of inductors, inductors are energy storage elements. So intuition is that the energy kind of goes into the magnetic field, and if you try to change the current, you have to change the magnetic field, and that kind of takes some time. You have to transfer some energy to kind of put that magnetic field into place, and then the magnetic field gives the energy back to you as you tear it down. It's a kind of potential energy. So inductors are energy storage elements. It's the potential energy that's stored in the magnetic field. And what they do is try to keep the current the same. So intuitively, they try to, and we'll make that more precise in a moment, they try to keep the current constant. Okay, more precisely, what actually happens is they will apply a voltage in order to try to maintain that constant current. So in other words, they kind of act as a voltage source for a short period of time in order to maintain a flow of current. So more precisely, they act as a temporary voltage source in order to counteract any changes in current. So if you want constant current, then you can put an inductor into your circuit in order to kind of provide a bit of smoothing out of that current. So that's one purpose of inductors. So in the next few videos, we'll go through and talk about their properties in more detail and do some problem-solving examples. But the key takeaway right now, this is what a real inductor looks like. It's a coil of wire wrapped around an iron core. And the most important equation, which you absolutely will need to remember, is that the voltage on the inductor is inductance times the rate of change of current. So V is L di dt, and you must know that equation.